All right, let's get started. Welcome everybody to today's webinar on photogrammetry. My name is Alex Razumov and I'm from Simon Fraser University. And I don't have my usual help today, so if there are any questions, feel free to type them into chat, but I won't be always paying attention to the chat. So once in a while, I'll check whether there are any questions, and perhaps the easier option would be to unmute and ask a question via audio. Today we're going to be talking about open source photogrammetry on HPC clusters. And photogrammetry, for those of you not familiar with the term, refers to using photographs to take measurements of what is being captured in two-dimensional images. So this term has been around for a while, but in recent years, of course, photogrammetry has primarily means the process of constructing a three-dimensional model by analyzing an unordered series of photographs or videos. So with the advent of computer graphics, now we're talking about essentially reversing the process of photography. So in photography, you have a three-dimensional object, then you take a bunch of photographs from different angles or perhaps with different lighting conditions. And then you, now in photogrammetry, you're doing the opposite. So you're going from a set of two-dimensional photographs to a 3D model. And traditionally, photogrammetry has been done with proprietary commercial software. So I talked to a number of researchers using photogrammetry in their workflows. And by the way, why photogrammetry would use photogrammetry in research? Well, a number of disciplines actually use it quite a bit. So I know folks in geography departments use photogrammetry, for example, for aerial imaging. People in archaeology might be using it for site reconstruction or artifact reconstruction and so on. And I also did a quick survey of problem support tickets. Let me actually make this a little bit bigger. Problem support tickets in our ticketing system. And the word photogrammetry came up quite a bit. So people were asking what kind of software they can run for photogrammetry on the clusters. And I thought it would be a good idea to actually do a webinar on this topic. So the most popular tool that people mention they use for photogrammetry in research is Metashape. So this is from the company called Agisoft. And the reason they use it, they can use it on the clusters is because it's multi-platform. There is a Linux version as well that you can run via command line. It's commercial, so it uses node-locked licenses, but the company provides educational discounts, so it's not that expensive from what I understand. So I've never tried it myself, but it seems to be a fairly popular choice. And there are other commercial packages as well for doing photogrammetry, but they seem to be not available on Linux. So that's why of all commercial packages, Metashape is the most popular one. There's also reality capture, but it requires, if you run it on a desktop, it requires Windows. And there's also a cloud option. Recap Photo from Autodesk. I checked, and the most recent version just runs in the cloud, which is obviously quite convenient, but you cannot run it on HPC clusters. So preparing for this webinar, I was curious what kind of packages, open source packages, support photogrammetry, especially command line photogrammetry, where you take, have a bunch of images and then ideally without any interaction, just convert these images into a three-dimensional model. So photogrammetry is very computationally intensive, whether talking about CPUs or GPUs. And so it actually makes it a very, very nice workflow to run on HPC clusters, because on HPC clusters, we have a lot of compute capability. And then if the software can run in parallel, you can actually utilize, scale up to bigger problems or run these photogrammetry workflows much faster if you run them in parallel. And so what I'm interested in for this webinar in particular is try to construct a workflow where I do everything via command line. So there is no GUI interaction. I'll talk about GUI a little bit towards the end, but ideally there's no GUI interaction. So you're looking essentially for a plug and play functionality. In go the images, right, a set of two-dimensional photographs, then you run your workflow as a batch job, and then out comes a three-dimensional textured mesh model. And so presumably in this workflow, you don't want to adjust parameters on the fly. So just try to let the software figure out what's happening, and ideally build the best three-dimensional model. So personally, I tried photogrammetry in the GUI a few years ago, but I've never tried, before starting preparing for this webinar, I never tried it on command line. So this is actually a big learning experience for me. And what I found in this process is that, so unfortunately, documentation for command line photogrammetry is pretty much almost non-existent with a few exceptions. So I'll mention these exceptions. But the problem is when you go to, so the packages I'm going to be talking about today, when I go to the documentation pages, they essentially tell you, well, here's the GUI, here's, here are the buttons, or go to File, Open, and then click this button, and so on. But this is not very helpful if you try to find out how to run these workflows in the command line. So essentially what I ended up doing for most part is I installed the software on the cluster in my environment. And then I looked at what kind of utilities are available for these packages in the command line. And then I Googled those and went to forums and try to understand what kind of flags and parameters and workflows they can do. And also, one thing that you'll see throughout today's webinar is that because these workflows are quite complex and there's quite a big software dependency chain, I didn't want to compile all of this via natively on the cluster. So none of the software is installed centrally on our systems. And then installing yourself is possible, but that requires quite a lot of compilation. So in this workshop, actually rely entirely on container images that I downloaded from Docker Hub, and then I converted them into Optane images that I'm going to show you how to run these images on our clusters. So how do you create these images from Docker Hub? Well, one easy way is to do it directly on the clusters. There are several limitations. You can actually run into problems while you're doing that. So I'm going to show you a better option on the next slide. But if you want to download an image from Docker Hub on the cluster and then convert it to an Optane image, an Optane containing image, what you can do is you can look into a cluster. For example, here is I'm showing the workflow on Cedar, but essentially the same workflow will work on, might work on other clusters. So there's one caveat is Cedar has internet online access from computer nodes. So you don't want to run these because these workflows on a login node, because doing this on a login node actually is quite CPU intensive, and login nodes are not really meant for anything CPU intensive. So you run it as part of a interactive job on one of the compute nodes. And unfortunately, most of our clusters do not allow online access from compute nodes, but on Cedar you can do that. So that's why I'm showing this workflow on Cedar. But basically here what I'm doing is I go into the Scratch folder, then I load the recent install Optane module 1.2.4 using this module load command. Then I start an interactive job, and converting these Docker Hub images into Optane images actually doesn't require a lot of, well, not that much resources. So here, actually, default amount of memory, roughly 4 gigabytes, is more or less sufficient. I ask for sufficient runtime, let's say 1 hour, and then 1 CPU task. And then once the job starts running, so I get the interactive shell inside the job, so this is quite important. You want to do this in this case. You want to use not the local last of file system, not Scratch, not project, not home. What you want to use is the local SSD attached to the compute node. And the way you access it, there will be a directory pointed to once your job starts running by the environment variable slum_tmp dir. And there, so in there you can actually create 2 directories, tmp and cache, and then set up a couple of environment variables for Optane, so that the Optane cache, so Optane cache is where your Docker Hub image goes into. So the cache directory is going to be inside this temporary folder, and then the tmp directory. So once you start running the Optane, some system file, well, Optane places some system files, and you probably want to place them on these into this temporary folder as well. And so the one caveat with this temporary folder is that it exists. So this slum tmp directory exists only for the duration of your job. So once the job finishes running, it gets deleted. So it's very important inside the job before the job finishes to actually copy out, so here in the last line, copy out the resulting CIF image, the Optane image, out into a regular file system. So for example, into one of your Scratch folders. And so then you run the Optane pull command, right? So you point to the Docker Hub image, and then then you say Optane pull the Docker Hub source, and basically it'll take 5, 10, 20 minutes, something like this. I'll create a local .c file, which is an Optane image. And so here I give the 3 commands. So these are the 3 Docker images I'm going to be using: OpenSFM, or ODM, and Mushroom. And in general, how do you go about finding these images? You can simply go to Docker Hub. So go to Docker Hub and then start searching for these softwares. I'm going to be talking about these specific tools. For example, ODM stands for Open Drone Map. right? So I just search for open drone map, and then you can actually find some results. So there are various images, for example, this one, right? So you can use this one or something else. So the ones I show on the slide are the actual Docker Hub images that I'm going to be using in this presentation. So these you can do inside an interactive job on the cluster. So sometimes, especially for larger images, you might still run into problems. For example, various permissions for files inside the container. And typically you solve these problems by being a super user when you are converting from the Docker Hub image into an Obtainer image. So obviously you cannot be root super user on a cluster because it's a multi-user environment. So what you can do in these cases is try to create these container images, convert them from Docker Hub images in a cloud VM. So if you go to our documentation, not sure if you're familiar with this, but if you go to our documentation, so docs.alliance.ca, and search for cloud, we provide a variety of cloud systems. So I'm using a cloud on Abutis at the University of Victoria, but there is also a cloud partition on all our HPC clusters. And essentially read this page if you're curious. So search for cloud and our documentation. You'll need to have a cloud project that is fairly easy to apply for one. And so here what I'm doing is I'm showing in this slide and the next slide, I'm showing how you can create a container image on a machine, on a virtual machine where you have root access. So typically when you create such machine, it comes with some storage, but it's usually something like 10 gigabytes by default, which might not be enough for large images. So what you want to do in most cases is, in addition to creating the virtual machine, you also probably want to create a volume. Let's see, do I have it in the slide? You want to create a volume right here, maybe 50 gigabytes in size, and then via the OpenStack interface, and the details are described in our help pages, attached to your instance. And then what you do, you format and mount the volume in a virtual machine. Then you install Obtainer, and you run the usual Obtainer pool, the name of the image you want to create, and then the source of the Docker Hub image in the as the last argument in the command line. So here are the commands, for example, that I use specifically to create one of the images. So once I create a spin up the virtual machine instance, and I create a volume and I attach the volume in the OpenStack interface in the web browser, then I log into my machine as root, essentially. And then I get the ID of the attached volume. And then here I set it up in the next line. So it's going to be something like virtue dash and then a long hashtag. And then I use that in the following command. So I format the volume, I create a mount point, and then I mount the volume under that mount point, because in this case it's /data, but I mean, it could be anything you want. And then I give write access to non-root to write in there. And then I install the Obtainer software. So you'll do it by these commands if you are on Ubuntu virtual machine. And then you run basically the Obtainer pull command, right? So in this case, I pull an official image from Alice Vision's project's Mushroom, one of the most recent images. And it takes something like, I don't know, 20, 30 minutes perhaps. And it will create an image which is roughly 4 or 5 gigabytes in size in this specific case. So let's get back to photogrammetry. So first step is image acquisition, right? So you're going to be converting a series of two-dimensional images into a 3D model. And it's actually quite tricky, so the image acquisition. So I actually, preparing for this webinar, I just took a bunch of very quick images of a small statue I have at home, a Buddha statue, and try to run photogrammetry software on it. And it has a very smooth surface, so it doesn't have any fine details or any colors, just single color and a polished surface. And what I found is I could not actually, I could build a 3D model, but the result is really bad. And the primary reason for this is because photogrammetry software in general doesn't work well with smooth surfaces and reflections. So ideally, you really want to have a model, a 3D object that are photographing from different angles that has lots and lots of small details, that does not have any reflections. And having a lot of small details actually helps you find match points. So match points are basically, in the between different images, there are overlapping areas, and then different points. Well, points that are easy for photogrammetry software to compute. So it looks for these common or match points, And then the more details you have in these photographs, the better. So how many images you should take? Well, for a good three-dimensional model, probably something like 60, 70, 80 images. So if you go into one of the tutorials for the package I'm going to be talking next, OpenSFM, and let me see, it opens right here. So if you go into their tutorial, they actually show an example where so they provide this data set for the tutorial, and it actually has only 3 photographs. And it turns out that if you run their workflow on just 3 photographs, it actually builds a fairly good 3D model. But the reason for this is because, as you can see, there are tons and tons of details. And the more details you have in such scenes, the easier it is, the fewer images in general you need. But in general, if you don't have as much fine structure, typically you need several dozens of images. So note that the more photographs you have, the slower, the longer it takes to process these images. And actually it does not scale linearly, scale more, I don't know what kind of power, so I didn't really do benchmarking. But if you do, let's say 100 images instead of 10 images, you will see that your computation time goes up by a factor of 30 or a factor of 50 or something like this. Also, you probably try to exclude points in the background. So ideally you would have, just a 3D model on a white background and then nothing else. But then maybe you'll have to edit your images manually to actually just have the the signal from the match points from your object in focus. And also you probably want to have all pictures in focus. So they repeatedly stress it in the documentation. So otherwise with unfocused images, it is much harder to do 3-dimensional reconstruction. So now the picture, the model I'm going to be using in the workflow today is this one. So it's a replica of a vase, and I took 84 images from different directions. And working with this in the photogrammetry software, actually post factum, I realized that I probably made a mistake with these images. I took a lot of pictures from different angles, but all of my angles are from high above, right? So I should have probably taken some images from low elevation as well, but it is what it is. So I have 84 input images that look like this. So in photogrammetry, there are 2 major components in the pipeline. The first one is called structure from motion, or SFM. And what it is basically you start with a series of 2-dimensional images. There is no information in the images about the camera location, or what is called camera poses in photogrammetry. So these are camera positions and orientations. So software has to figure it out itself. So it looks for overlapping parts of images, then find common or match points, and then it tries to convert those points in 3D, and at the same time to reconstruct in 3D these camera points. So this is what is called structure from motion, and the outcome is a set of calibrated cameras as well as a sparse point cloud. So it's called sparse point cloud because it's essentially a set of match points that are present in multiple images, and then it tries to map those points into 3D. And then the second part of the algorithm is dense reconstruction, or multi-view stereo. So here you take all these camera poses and the sparse 3-dimensional cloud, and then you try to build more detailed 2-dimensional surfaces in 3D, right? So the outcome is going to be a dense point cloud, dense geometric surface. And then the outcome, so in terms of files, the outcome is going to be a mesh file, as well as a projection of textured images onto this mesh. So for the first part, the most popular package is called OpenSFM. You can find details for this on their website. Really good project, a lot of documentation, but unfortunately, again, documentation is mostly related to how you run these, not via command line, but via GUI. So obviously it's open source project. You can download and compile the source, and then you run it. So I'm going to show how to run the pipeline in the next slide. And then in addition to the input images, you can also supply a list of ground control points. So these are essentially a set of points with 3-dimensional, usually geographic coordinates like latitude and longitude. And so these points are useful for aerial imaging, right? So if you're doing just a small scale artifact, then probably you don't need the ground control points, but you can use them if you want for larger scale photogrammetry. And then there's also a config YAML file. So that's the YAML file with a bunch of parameters that you can use to override the default values. So one of them is number of threads to use. So this software, OpenSFM, it runs a single Unix process, but it can run it multi-threaded. So you can have you can have benefit from having multiple cores if you run on the same compute node, using multiple cores on the same compute node. And then there's a whole bunch of other parameters. So there's actually a good discussion in one of the forums I found, where they go through the parameters and they tell you exactly what will happen if you modify these parameters. So really good discussion. So how do you run it in cluster? Well, because we're trying to do this non-interactively via batch jobs, you obviously have to write a script, a Slurm script to submit a batch job. So typically you ask for number of CPUs. So the image that I downloaded, even though the software that I'm mentioning, I mentioned in the previous slide is multi-threaded, the image that I downloaded seems to have to be able to run just on a single thread. So maybe I would have to recompile it. I didn't try to recompile the software inside the image, so I just use it as is. And it can run just, so in that image, it can run just on a single CPU core. So I'm asking for a single CPU per task, then maximum runtime. So the V's example took about, so I ran it a couple of times on CEDAR. In one case, it took 1 hour and 40 minutes. In the other case, it took 2 hours and 23 minutes. So I am asking here for 3 hours. Then it does not require a lot of memory. So something like 3,600 megabytes should be sufficient. So if you run on production classes like CEDAR, you have to specify your account as well. And then you load the software. So here what I'm doing is I'm deleting in the target directory, I'm deleting all previous results. So basically in this command, I'm deleting everything in the current directory, well, in the base directory, except for the images subdirectory. And then I run the entire pipeline. So I run via obtain exec command, right? So obtain exec, some flags, then point to the CIF image, obtain the image, and then inside the image, I'm running this OpenSFM run all command pointing to the V's subdirectory. So this runs the entire script, will take 1 hour, 2 hours, 3 hours, something like this, depending on the complexity of your scene and the number of images. And then underneath, it actually runs a bunch of computations. So in fact, if you don't want to run the entire pipeline, you can actually replace these lines. So instead of having this OpenSFM run all script, you can have individual scripts. You can actually replace this line by individual lines, just pasting this stuff inside the obtain exec commands if you want, if you don't want to run the entire pipeline. And then at the end, after it finishes running, you can look for files with the .pli extension. There will be several of them. And so the final result is actually going to be something a little bit better than the sparse image. Will also contain some additional points. And then you can load these points, download your computer, and then load them into your favorite mesh visualization program. So I'm going to show you now how to run the demo on for the Boolean dataset on. So that's the dataset with 3 images that comes from their tutorial on the training cluster. So the training cluster is a cluster I'm using we're using for teaching HPC, various command line things and so on. So basically, the idea is that it's a cluster that has exactly the same software environment as our production clusters, but it's much, much smaller. And then here I'm going to also do it because this is my own, virtual cluster. I can actually run things interactively there immediately. I don't have to wait in the queue. And then what I'm going to do is I'm going to cd into the Scratch OpenSFM directory. So in this directory, I have the V's images subdirectory. So here I have 84 input images. And then I'm going to load the obtainer module. Right here, loading the obtainer module. And then I'm going to start the interactive job, a single CPU, half an hour runtime. So this simple Boolean model has just 3 images, so it's going to take something like 3 minutes to actually run it. So 30 minutes should be more than enough. And then 3,600 megabytes of memory, so give me an interactive shell. So here I'm now inside a compute node, node 1. So then I'm going to erase all previous results. And then what I'm working with is, so my V's data set is right here, right? Inside images folder. And then I'm simply going to copy sorry, not V's. I'm going to be working with the Boolean data set. So I'm going to copy the Boolean data set into the current folder. And oops, no such file directory. Because I need to start the obtainer, of course. I need to start the obtainer, the shell inside the obtainer. And then I'm going to copy everything from the built-in directory, built-in just 3 images, sorry, into the current directory. And the reason I'm doing this is because in order to run this workflow, I must be on a writable file system, right? So basically, I'm copying built-in. So I won't be using base in this demo. I'm running on built-in. And so inside built-in, I have, let's say, 3 images right here. And then to start the pipeline, I'm simply saying open SFM run all on built-in data set, and then it will just start the pipeline. So I'll run in the background while I talk. It's going to take something 3 or 4 minutes, and then at the end, I have a nice PLY mesh file. So I'm going to show you this file. On my computer. For the Vase directory with 84 input images. So I'm going to be looking into TMP, Photogrammetry folder, open SFM, into Vase, and right here the output image, the output file is a .ply file. So I'm going to load it into ParaView, which is a standard scientific visualization tool. So apply. So here's what actually I misspoke. It's not a mesh. So it's a point cloud, right? It's a point cloud, which, you know, in my case on CEDA, it took something like 2 hours to obtain. So I can actually color it by the available color. So here, the thing is that you see ParaView was not creating for looking at the results of photogrammetry. So it has a color variable, but the color variable, so it's 10-bit color. So there are 3 variables, R, G, and B. They go from 0 to 255. But because ParaView just understands this as a single number, so it constructs the vector out of this, and then the magnitude of the vector goes from 0 to 440 in this case, right? So it's not really a real true color, so it's, you know, some function of R, G, and B. But basically here you see you have a fairly dense point cloud. There are how many? 1.6 million points, right? And so this is what you get from these open SFM photogrammetry. So while still running, let's talk about the next component. So the second component is now building dense point cloud, and then on top of this dense point cloud, build the meshes, and then apply a texture to these meshes or to the surfaces. So a very popular package, open source package for this is called OpenMVS, and it's open source. It can run on Linux, so therefore you can actually run it via command line on the cluster. So again, documentation is somewhat sparse, and if you go to documentation, you will see that it it describes entirely the process on in a GUI, which is not what we want. So instead of showing the workflow here, you can run it if you want. I'm actually going to change gears a little bit, and I'm going to show you 2 packages, OpenDroneMap and Mushroom, that let you run the entire pipeline. So both SFM, structure from motion, and the dense point reconstruction as a single pipeline entirely on the cluster. So one is called the first one of these packages is called OpenDroneMap, also known as ODM. Really fantastic package. And the way you run it on a cluster, so in this case, again, I did not compile it. I actually took a Docker image, converted to a container image. And then here, again, I'm showing how to test it on the training cluster. By the way, here, with the previous software, it actually finished running. And then if I look for all.ply files, I'm going to say find, actually in the built-in database, look for all files with the .ply extension. And so here is the result. And in this case, it built, actually, let me do ls-lh. So it built the 14 megabyte, so as you can see, fairly detailed point cloud out of just 3 images. And the reason why I could use only 3 images, well, because they have a lot of fine details. Anyway, so now talking about OpenDroneMap, the entire photogrammetry pipeline. So the way you run it on the cluster, won't show the demo because otherwise we will run out of time, and actually the demo actually takes a while. But if I were to show the demo, I mean, it's very similar to the previous example. So I would load the Obtainer software via a module. Then I will start an interactive job. And in this case, OpenDroneMap, this image I'm using is actually capable of running in parallel. So actually, why don't we demo it? So because we already are on the cluster. So here I'm going to say I think I already loaded the Optina module, but let's just do it again. And then I'm going to start an interactive job. So this time I'm asking for 2 hours maximum runtime and 8 CPU cores, right? So this will take me on one of the nodes, gives me a shell on a node. And then let me actually paste these commands. So in case I have some files from the previous workflow, I'm going to delete them. Otherwise, software might actually stay and might actually crash. So here we are starting with, we placed the images into a file with images in the current directory, right? And then I start interactively the shell inside my ODM Optina image. Oops, Optina, oh, it's not there because I need to go, actually, sorry, into OpenSFM. Yeah, and then I should probably, sorry, I was in different directories, so I probably want to rerun these commands once again. So that, and this command, just in case I have some intermediate results from the previous run. And then I'm going to start the shell. Oops. Oh, still did not transfer. Okay, sorry about that. Well, let me, yeah, now I'm in the proper ODM directory. So let me run 354, 355, 355, and then 356 again. And then I'm going to do, so now I should have the, in this directory, yes, I do have ODM latest CIF image. So I'm going to start the shell inside this image right here, right? And then inside the shell, it gives me access to, so the code is right here. It's a Python script, as you can see, and I just run this entire command. So if you run this command without any flags, in this case, I'm passing the AND with MOS texturing flag, then, so if I run it without any flags, it will just run the script and we'll go through all the entire photogrammetry pipeline. There are 12 stages, and I put them into 2 columns. So the second column is actually important when you do drone mapping, 3D reconstruction, when you do aerial imaging, right? So in our case, we're not really interested in georeferencing or in reconstructing the surface elevation map. We're just interested in photogrammetry for the vase, just for the vase. And all we need is the steps in the first column, ending with computing the two-dimensional, applying the textures to our two-dimensional polygonal surface. So we see and with NBS texture and face. It'll actually run for a while, so I won't wait until the end because that will take a couple of hours. So here, if you were to run this on a production cluster like Cedar, you probably don't want to do it interactively. You want to do it as as a batch job. So in this case, you run a script. They will probably look something like this: ask for 2 hours, ask for, let's say, 16 CPU cores, 3,600 megabytes of memory per CPU core, and then have your commands to load the Optina software, just in case erase all previous results, and then run the pipeline. While the pipeline is running, by the way, you can, actually, let me show this. This is useful. So let me restart the shell, and let me restart the pipeline. So while the pipeline is running, in a different window, I can log into the cluster. And so here you can actually, while the the compute code, is running, or I should, okay, yeah, I would need to reduce do some cleaning there. So I won't do this now. So while the code is running, you can actually attach, open a separate window, log into the cluster where your job is running, and then you know the job ID, so you can attach to the job. So open a shell in a currently running job. So that's what srun command will do. And then you can do things like htop or ps or top, and it will actually show you CPU usage. So in this case, you will be able to see what step of the pipeline is currently running, of this pipeline that you saw in this slide is currently running, and I can actually see CPU usage. So it will run in this open drone map a particular image software you can run. It will run only on CPUs. It will not utilize GPUs. And then at the end, what you get is a bunch of files. So you'll get the sparse point cloud. You'll get the dense point cloud, as well as the polygonal mesh, texture on top of this mesh, and then the texture will be pointing to materials. And materials are simply PNG files, so the images that this photogrammetry ODM software decided to to use for your particular three-dimensional model. So let's take a look at the results. So in my case, I have results on my computer inside UDMV's directory. So in here, I have a bunch of files. So as you can see, I have let's first take a look at the dense point cloud. So that's the scene dense file. So let's see, scene dense it's in the current directory. So let me try to open it. And by default, PLY will open in ParaView. So let me open ParaView, and then I'm going to show you the textured model as well. So here is, let me actually delete the old one. Delete, then go this guy, reposition. So here is what it looks like when you run it through OpenDroneMap, right? So this is a dense point cloud. And again, this does not have a mesh. It has just the points, in this case, 900,000 points. You can color them by force color, right? So this is what this face looks like. But more interesting, you can actually look at the textured map. So the textured map, so the problem with displaying a textured map in ParaView, it's actually quite difficult to do that because in ParaView, you can apply one texture per polygonal mesh. And in this case, what we have one mesh. So in the object file, actually, let's try to load this in ParaView. And so you will see what I mean. So let's take this mesh, and then let's open it in ParaView. Oh, applications, ParaView, and then, oh, it actually refuses it. Cannot be opened for unexpected reason. Okay, well, never mind. So, and then the problem with displaying this in ParaView is that it lets you apply only one texture per polygonal mesh. But in this case, we have a single mesh, but we have these multiple PNG texture files. And so in ParaView, you can display it, but it's actually a little bit tricky. So instead of displaying it in ParaView, I'll actually show you what it looks like in MeshLab. So MeshLab is another open source software. Let's see, I'll just open this file. And then you will see the result of the 3D mesh reconstruction from OpenDroneMap, as well as the texture on top of it. So this is what I get, right, as the final step of running this OpenDroneMap pipeline on Cedar. So as you can see, there is a lot of artifacts from reconstruction. So one other thing is that I was not very careful. Let me go to my slides. Is if I go to my images, you see that at the base of the images, there are still quite a lot of reflections, and this introduces artifacts into the 3D reconstruction. But fortunately, I can actually add these artifacts. So what I can do is I can, in MeshLab, I can say select vertices like this, for example, and then I can say delete these vertices, right? So I can actually clean it by hand. And then, I can go through all of this, and then the result, actually, let me show you the cleaned image. So where's my MeshLab? I'm going to show you the cleaned image, what it looks like. So the cleaned image will look something like this, which is actually, fairly decent image. So I forgot how do I pan it? So it looks like this, right? And this is actually a 3D mesh with the texture applied. And if you're curious, what do the texture file looks like? Well, they're PNG images. So here, if I just show all the PNG images, this is what they look like, right? So they're not particularly human readable, but then MeshLab maps these onto the polygonal surface, and then you get a fairly nice result. All right. So at this point, before I go to the next pipeline, are there any questions? All right. Next, let's take a look at Mushroom, which is another popular open source 3D reconstruction software. And it actually comes from an online project called Alice, what is called Alice Vision. You can read about it more, but the idea is a nonprofit organization whose goal is to popularize tools for three-dimensional photogrammetry. So really cool project, and Mushroom is one of their tools. So it's built on top of open structure for motion library that I mentioned before. But in addition, it also, so the second part, reconstructing dense point clouds and applying textures, it actually can run on CUDA. And in fact, it turns out that in order to run this Mushroom software well, you actually need a CUDA-enabled GPU. So it has to be an NVIDIA GPU, so you can run it on your own laptop, your own desktop, but then you need an NVIDIA card. So you can run it without GPUs. You can run it entirely in software, but it turns out it uses draft mashing from the structure from motion step, from the first step in the reconstruction, and the result is going to be very, very poor. So I try to play with it, but it turns out if you do it entirely on CPU, so not on a GPU, then the output, the output quality is going to be really poor. So you want to run it on NVIDIA supported GPU. So our classes have GPUs, right? For example, on CD, you can actually submit a job asking for a GPU node, and there it will run just fine. So on Docker Hub, another thing that I run into, another problem that I run into, there is a bug in the most recent official versions of their software on Docker Hub. So if you download their tools and try to run a cluster, you will run into this error message: assertion for row and columns failed. And basically what it means, I'm not sure why it runs in Docker Hub, but in Aptina it doesn't run. So I know actually what happened. So when they compile their software, they forgot to turn off the debug flag. And actually here, what it's doing, so it's working with some internal with some two-dimensional table, and then it tries in two-dimensional array, and then it tries to write into that array, and it mixes. So they made an error somewhere where the order of rows and columns is changed to the opposite order. And then to the output image, to the result, it does not matter because they are doing this inside C or C++, and they're just using pointers. And so the result is, the result is still the same. It doesn't matter. It still writes into that memory block, just in a different order. But they forgot to turn off debug flags, and then the resulting Aptina image crashes. Actually, tested a couple most recent images, and both of them have this bug. So what I ended doing, instead of using the official images, I using a third-party Mushroom image on Docker Hub that is actually much smaller. It's only 0.5 gigabyte, and it doesn't include the most recent version. Now it just goes back several versions, but actually works very nicely and reconstructs a very nice three-dimensional model. So the only thing is I have to remember that instead of using the what is called Mushroom batch utility in the most recent versions of Mushroom, it has an old name, Mushroom _photogrammetry. So just keep that in mind if you try to use the more recent versions. And overall, the experience was really great. So basically what I had to do is I simply submit a job. So I load the Aptina module, and then I run this job on a GPU node, right? So in this case, I submit a batch job. I'm asking for a GPU. So here, number of GPUs per node, 1, right? So on CD cluster, we have NVIDIA CUDA capable GPUs. So the software runs just great there. And then I'm asking for 1 hour maximum runtime, actually finishes under 1 hour, 1 GPU, 8 CPU cores, and then I run the pipeline. So I put images into the current directory, subdirectory these /images, and then the results are going to be written into a directory in the current working directory, subdirectory called results, right? And so here, this is all, this entire block of code, it's the job submission script, right? So inside the job submission script, I create a script called run.py. Actually, it should be run.sh, right? Not sure why. Yeah, it's a bash script, so I should modify this. It should be run.sh, not a Python script. And so inside the script, I inquire about the current GPU that was assigned to me inside this job, right? So basically there it will say typically a P100 GPU is available to you, it has so much memory and so many cores, etc. Then you also need to set up this environment variable. So for some reason their code actually requires this localization variable, otherwise it will just crash. And then you create a results directory. So if you ran this previously, you have to make sure that you remove everything from the results directory, otherwise your code will crash. And then you just run the Mushroom _photogrammetry tool using the all input images from this directory, and then writing these results into the results subfolder. And then you run it, and it will take under 1 hour on 1 GPU and 8 CPU cores, in my case with 84 input images. And then you look at results. So one of the nice things about Mushroom that it will output a tons of log files, and these log files will actually contain timing, right? So in this case, I run it on CEDA. My total time, so that's the wall clock time, was 33.5 minutes. And then if you look at individual steps, so in various logs and subdirectories, you can actually see the timing for the 12 individual steps. And as you can see, there's a single step that requires CUDA that took 600, in this case, 688 seconds, so roughly, I don't know, 11 minutes, right? 12 minutes. And then, so you see that roughly 1/3 of the time was spent inside a GPU. And then 2/3 of the time inside this run, there was no GPU calculation code, computing involved at all, right? So that means that 2/3 of the time, my GPU was just sitting idle, which is probably not a good thing on a cluster because GPUs are in very high demand, and most of the time inside this job, my GPU was not used, right? So how to solve this problem? Well, very easy. Instead of submitting a single job, you submit 3 jobs, one at a time, right? So first you run the CPU pod, then you run the GPU pod, and then you run the CPU pod again. So that's how you would do this, right? So here I'm submitting a CPU-only job. I'm asking for 16 cores and maximum runtime of 30 minutes, right? And then instead of running the entire pipeline, I just run individual steps. So camera initialization, feature extraction, image matching, all the way to, but not including the dense cloud. So the dense cloud scene, so depth map or dense cloud scene requires CUDA. So that I run into, so once my first job finishes running, I submit the second job, which includes, which will run now on a GPU, right? So I'm asking for a single GPU, 8 CPUs, maximum runtime of 30 minutes. But again, in this case, I'll probably finish in under 10 minutes. And then it's, I run this just one step, dense map reconstruction. And here, notice that, by the way, the way I do this, you have to, so previously all steps were called camera init, feature extraction. And then here I had to say dense map _1. So depth map will actually not work. It will give you an error message. And so, all small details like this, they take a lot of time to figure out, especially if they're not documented. These things are not documented at all. And so I hope that this webinar actually, gives you all these fine details, which are very important. Otherwise, you will spend a lot of time, figuring why you get all these error messages. And then once the GPU part finishes running, now you are back to running on CPUs only. So you run the rest of the pipeline, and then the final step, publish. What it does, it actually doesn't do any computing. It takes the results from meshing, from computing textures, and then it copies all these results along with the log files into a directory called results, right? And then you simply take everything inside the results directory, right? So here I'm interested only in the file called status and the files called log, and also in everything inside the mash room cache directory that contains the actual results. And then I compress that into a tar.gzip archive, results of tar.gzip that I download to my computer, extract it, and then I look at the results. So let's check the results. So here I need to go into Mushroom. So go to levels up and then Mushroom, and then into this directory. So here's what the results look like, actually results folder. That's what they look like, and there are only 3 files. So in this case, unlike with the previous Open Map software, Mushroom decided that there is just a single texture that it needs to apply, but it's a much more complex texture. So I'm not sure how these maps, so here's what this file looks like. I'm not sure how this file actually maps to 3-dimensional models, because just looking at this texture, it's not obvious to me what is what. But if I open the end result, so here is the textured mesh object. So it will open in Mushroom. And this is what it looks like. So in this case, I didn't do cleanup. As you can see, there is quite a bit of artifacts, especially at the base of the vase from all those reflections. But it still gets a very nice does a very nice reconstruction, and I get my textured 3D model. All right. So if you want to more control over the pipeline in Mushroom, you can actually do this by, so if you run Mushroom itself, it actually outputs a lot of stuff into the logs, and it can actually see the underlying exact commands that it runs. So underlying runs things like, for example, at least vision camera init, and there are all these parameters that it passes to this utility, and you can actually play with these parameters. Let's say allow single view and other. So this is the very first command, but then when it comes to other command, lots and lots of parameters that you can play with and hopefully improve your 3D results. All right. So that's all I wanted to show. So we still have 10 minutes for questions. Basically, my goal here was to show you the details, how you can run these packages, OpenDroneMap and Mushroom, the entire pipeline, entirely via batch jobs on the cluster. Of course, you can also run these on a command line if you have, let's say, a Linux computer, and you just want to do it, the entire pipeline in the command line. So with these tools, you can also do GUI. So most of the tools that I mentioned to you, they also have a GUI component. So typically what you do is you start a GUI server, and then you connect to the server from a web browser. So typically you do that, and the original implementation is you do this on your own computer, right? So you start a local server, then you connect to in a web browser, you connect to a local host and a certain port number, and then it loads some GUI where you can have sliders. You can delete, for example, some match points and et cetera. You can clean up your pipeline a little bit via GUI interaction, and you can also do the same on a cluster. So in this case, you will submit an interactive job, then manually start let's say, a open drone map server on the cluster. Then you will create an SSH. It will create SSH port forwarding, connecting a port on your computer to the remote port on a compute node inside your job running your server, right? And then you open a local browser pointing to your local port, and then that will give you interactivity via a GUI inside your web browser. So the only downside of this is that while you're doing all this interactive, I don't know, mesh cleaning, for example, it will have the process running in the background, even though you're not on the cluster, even though you're not doing anything, right? So it's very easy to get into a scenario where you're wasting resources, where things are just sitting idle on the remote cluster, right? For that reason, I really don't recommend that you do these interactive workflows on the remote machine. Perhaps what I can do is you can split your workflow where you run some pieces locally in the GUI and then offload CPU intensive parts via batch jobs doing these, parts of these command line workflows that I showed you previously. So there are several other open source projects that I did not have time to check. So they're listed here. I have tried Regard 3D several years ago, but I have tried it not as a command line, but as a GUI, and the results were pretty bad at the time, so I have not tried it recently. I know that these two, CoolMap and MicMac, can actually run in Linux by command line. So that means that in principle, you can try to run these in the command line as a bad job on a cluster, right? But I just did not have time to go into these, so I just concentrated on OpenDroneMap and Mushroom. But in principle, you can try those as well. If you run into any problems with these or with essentially anything doing photogrammetry on a cluster, let me know. So my email is on the front slide, alex@razumov@westgi.ce. And then there's also a recent article which I found quite useful. It's from 2020 and was updated for 21, which compares these tools. So they're actually not focused on command line, they're focusing on the GUI, but still it gives a pretty good comparison of these various open source photogrammetry tools right here, right? And then a fairly short article, but then it has some nice links and some nice results. So I think I'm going to stop here. I'm going to put my summary slide here, and then I'm going to stop the recording.